Our universe appears to be expanding and cooling, having originated some 13.8 billion years ago in a hot Big Bang. However, it's plausible that what we see from inside our universe is simply the result of being inside a black hole that formed from some parent universe. If the black holes that form in our cosmos give birth to baby universes, perhaps we arose from the formation of a black hole ourselves. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. One of the biggest existential questions that has puzzled humanity for as long as humans have been around is simply, where did all this come from? After countless centuries of wondering and speculating, the 20th century brought with it our first scientific answers to that question. We learned that distant objects in the universe are speeding away from one another, evidence that our universe is expanding. We discovered that more distant galaxies appear younger, less massive, and with greater rates of star formation, evidence that our universe evolves with time. And we discovered a near uniform background of blackbody radiation, evidence of an early, hot, dense, radiation-dominated state. All of these puzzle pieces, when put together, indicate that our universe originated from a hot Big Bang some 13.8 billion years ago. But our universe has a very curious property that not everyone appreciates. If you add up the mass and energy of all the particles contained within the visible universe, you can ask the question, how big would the event horizon of a black hole with this mass be? And the answer, perhaps surprisingly, is very close to the actual horizon size of the observable universe. Additionally, there's another related idea, made famous by Stephen Hawking, that each time we create a black hole in our universe, it could give rise to a baby universe that's only accessible to an observer that crosses inside that black hole's event horizon. Could our universe, then, actually have been spawned by a black hole that was created in some sort of grand parent universe, and do we give birth to a new universe each time a new black hole is created? It's a fascinating idea worth exploring. Here's what the science, at present, has to say about it. The defining feature of a black hole is the existence of an event horizon, a boundary that tells a very different story for an object outside of it versus one inside of it. Outside of a black hole's event horizon, any object will experience its gravitational effects, as the space will be curved by the black hole's presence, but it can still escape. If it moves fast enough or accelerates quickly enough in the proper direction, it won't necessarily fall into the black hole, but it could break free of the black hole's gravitational influence. Once an object crosses over to the other side of the event horizon, however, it's immediately doomed to be subsumed into the black hole's central singularity. Because the fabric of spacetime is severely curved inside a black hole, an infalling object will reach the singularity within seconds of crossing the event horizon, growing the black hole's mass in the process. To someone located outside the event horizon, the black hole appears to form, gain mass, and grow over time. What does this have to do with our universe, though? If you were to take all of the known, measurable forms of matter and radiation in the observable universe, you'd have to add up all of the following. Normal matter, made from protons, neutrons, and electrons. Neutrinos, ghostly fundamental particles that rarely interact with normal matter. Dark matter, which dominates the universe's mass but has so far eluded direct detection efforts. Photons, or particles of light, which carry energy from every electromagnetic event throughout cosmic history. And gravitational waves, which are created every time a mass moves and accelerates through the curved fabric of spacetime. At the farthest limits of what our instruments can possibly detect, we can see up to about 46 billion light-years away in all directions. If you add up all the energy from all of these forms throughout the entire observable universe, you can arrive at an equivalent mass for the universe using Einstein's most famous relation, E equals mc squared. Then, if you like, you can ask a rather profound question. If the entire universe were compressed into a single point, what would happen? The answer is the same as it would be if you compressed any large enough collection of mass or energy into a single point. It would form a black hole. What's remarkable about Einstein's theory of gravity is that if this collection of mass and/or energy isn't charged electrically and isn't rotating or spinning, i.e., without angular momentum, the total amount of mass is the only factor that determines how large the black hole is, what astrophysicists call Schwarzschild radius. Remarkably, the Schwarzschild radius of a black hole with the mass of all the matter in the observable universe is almost exactly equal to the observed size of the visible universe. That realization, on its own, seems like a remarkable coincidence, raising the question of whether our universe might actually somehow be the interior of a black hole. But that's only the beginning of the story. As we dive deeper, things get even more interesting. Then, if you like, you can ask a rather profound question. If the entire universe were compressed into a single point, what would happen? The answer is the same as it would be if you compressed any large enough collection of mass or energy into a single point. It would form a black hole. What's remarkable about Einstein's theory of gravity is that if this collection of mass and/or energy isn't charged electrically and isn't rotating or spinning, i.e., without angular momentum, the total amount of mass is the only factor that determines how large the black hole is, what astrophysicists call Schwarzschild radius. Remarkably, the Schwarzschild radius of a black hole with the mass of all the matter in the observable universe is almost exactly equal to the observed size of the visible universe. That realization, on its own, seems like a remarkable coincidence, raising the question of whether our universe might actually somehow be the interior of a black hole. But that's only the beginning of the story. As we dive deeper, things get even more interesting. Something remarkable happens when you look at the equations that govern a black hole as well. If you start just outside the event horizon and escape to an infinite distance away from the black hole, you'll find that your distance, r, goes from r, the Schwarzschild radius, to infinity, infinity. On the other hand, if you start just inside the event horizon and track your distance from the black hole to the central singularity, you'll find that same distance, r, instead goes from r, the Schwarzschild radius, to 0, 0. Big deal, right? No, it actually is a big deal, for the following reason. If you examine all the properties of space outside of a black hole's event horizon, from r to infinity, and compare them to all the properties of space inside the black hole's event horizon, from r to 0, they are identical at every single point. All you have to do is replace the distance, r, with its reciprocal, 1/r, or, more accurately, to replace all instances of r/r with r/r, and you'll find that the black hole's interior is mathematically identical to the black hole's exterior. Smarter, faster, the Big Think newsletter. Subscribe for counterintuitive, surprising, and impactful stories delivered to your inbox every Thursday. Fields marked with an asterisk are required. Email. It's almost like taking a spherical orb that's 100% reflective, a perfect mirror, and noticing that the entirety of the universe that's located outside of that sphere is now contained, albeit distorted, in the mirror image that's reflected on the sphere's surface. As our understanding of the universe has improved and been refined over the past few decades, two new discoveries have rocked the foundations of cosmology. The first was cosmic inflation. Instead of arising from a singularity, it now appears that the universe was set up by a rapid, relentless state of constant, exponential expansion that preceded the hot Big Bang. It's as though there were some sort of field that provided an energy inherent to space itself, causing the universe to inflate, and only when inflation ended did the hot Big Bang begin. The second was dark energy. As the universe expands and becomes less dense, distant galaxies start to recede from us at an accelerating rate. Once again, albeit with a much smaller magnitude, the universe behaves as though there's some sort of energy inherent to space itself, refusing to dilute even as the expansion of space continues. People have speculated that there might be a connection for as long as inflation and dark energy have both been around.
Yeah, yeah.